Now, I will make this very quick, also because I don't really know your current level. It is possible that I will teach you MPI and already know everything. And the same may very well go for these slides that I'm presenting you, which are just a brief introduction to the world of supercomputing in case you don't have a clear idea of what it is and what it does. Or it can be a reconfirmation in case you already know everything there is to be. And there are also my colleagues that are going to tell you more in the following days. And then we will discuss a little about what Leonardo is. This cluster that you tried with various degree of success to connect in during this first part. So, high performance computing is born with the idea of assisting scientific research of any fields, of many fields, of all the branches of scientific research that you can imagine. There are applications in science computing. So you can imagine that you want to simulate something that is very large, like cosmology, like astrophysics, or weather forecasting. You can imagine you want to work in the world of the very small, like chip design, drug design, and molecular dynamics, especially everything that is involving the, for example, what is going on with a set of molecular and particular initial conditions given specific amount of time. You can perform simulations about what is absolutely too complex for us. You can't reproduce a hurricane in laboratory, for example, but you can also always test what are the expected behaviors in the supercomputer, or everything that is too dangerous or too expensive and is not worth trying other means. So any classical field of scientific research is, in a way or another, working with supercomputers. There are modern trends. You may know about them more than me. So everything that is involving AI, for example, or quantum computing is another field that is exploding. Everything is, a lot of things are starting to get the interest of the high performance computing world with architectures studied for those specific cases and a lot of study, or even in the hardware aspect of the discussion. We start from here. This is the very well-known von Neumann model. It is the beginning of the world of computers. The idea is pretty standard. We have a control unit and a memory on which can connect every device, and the operations are sequential. I need to perform a particular operation. I fetch the operand, I fetch the operator itself, I compute, I store in memory, and I return in output the result. So there is a sequential set of instructions that are performed one by one by this complex model of computing that has always worked for quite a lot of time, and also was the model that gave birth of the first supercomputers, which whose definition is not that complicated. We talk about supercomputers as the most powerful computers available in a given amount of time. So it is not something about how the architecture is built. It is not something about what kind of material do I expect, what kind of internal design modeling, nothing of that sort. If you have to prove that you are the most powerful computer at the time, or among them, you have to prove that you are focused mostly on computation. There are many aspects that computer designs want to look into. If you work with supercomputers, you want the best architecture possible at the time for performing simulation and computing with the best performance possible. And for a good amount of time, we were all in the hands of the Moore's law. Moore's law is an empirical law. It is something that was observed and more or less true for a good amount of time. It was just saying that every 18 months or so, the complexity of the devices, of the processors, of the single processors were doubling. And so transistor chips, computers more powerful with a power that is double every time were released with that particular time lapse. And that was true for a lot of time until we reached some kind of barrier. Like we can't go any more than this with a particular with this particular mindset, because we are starting to face real problems. Like if you are only focusing on creating chips, processors that are faster, we now know that we can't go smaller than a certain size, because we started to work in the range of atoms. We are getting transistors that are of atomic dimensions, and this also gives you unwanted effects like quantum effects, and most importantly, the problem of heat dissipation. The more performant the single processor is, the more overheated it gets, and the more problematic it is for you maintaining, for keeping working. And also it is a problem in terms of environment, because it requires a lot more of energy, and in terms of cost. So it is not something that we want, and we may want to try something different. Also, this is not the only problem. Actually, it is a smaller problem related to other problems. The main problem is the bottleneck between the power of the single processor and the problem of memory access. A lot of architectures are really efficient when they're performing that particular computation, but they spend too much time in memory access, in dealing with input and output, or just working with their RAM memory. It is the main problem, because the technology of processors goes way faster than technology of memory banks and memory access. So concepts like bandwidth and the latency are getting even more important than concept like basic performance. There are countermeasures like cache units. I suppose that you more or less know about a cache unit. It is a smaller size of memory, where the data, once it is picked by the main memory, it is stored there together with their neighbors, so that we can exploit the advantages of the principles of local speciality and local temporality. I hope I said that right. The idea is that if I need a particular data, it is highly likely that I will need it again in the near future. So it is stored in cache when I can easily access it. And the idea is that I need that particular data, it is likely that I'm going to need also the data that is close to it. For example, I pick an element of an array, it is likely that the next loop iteration, I will need the next element of the array. So I put immediately together in the cache line, and I get a cache hit when I find the data there, a cache miss if I don't find it there, and I have to move to the mainnet. These are standard architecture principles, and are just one of many ways of dealing with memory, which is always a main problem. So at a certain point in time, given that working on a single processor wasn't enough, people started to think about parallel computing. What if I take many processors, many cores, many tasks at once, and make them all work in the same program to reach together the same solution? This was the main idea of parallelism. Parallelism can be done in many levels: instruction level, and vectorization, and hyperthreading, which are more or less still at core level. And then we can increase the number of cores. We can divide our problem in many sub-problems, and each CPU takes care of a particular aspect. Think of weather forecasting. I can divide my map in various cells, and each cells is dealt with from one task or one processor, depend on the model that you're working on. In any case, the many parts of the supercomputer can together redesign the map. And that's more or less how it works. But you have in this example, you have to be aware of what happens in the border, because your border is affecting the border of the cell, so of the processor that is close to you. So you need to communicate. You need communication between tasks and cores, and this is where parallel paradigms are playing. And these are things that you are seeing later on in the school. Since they have to communicate, it is important the topology, the network, actually. It is important also in terms of hardware. All those cables connect each part of the supercomputer to another part, so that every the compute node is basically a set of a number of CPUs and a unique bank of memory that they can see in shared memory way. So the network becomes important. Every node has to see every other node, and the topology becomes something relevant because it may affect the performance of your code. So there are many examples. For a while in Cineca, we had clusters with torus technology. You can imagine periodic boundaries that are limiting, not limiting, they are connecting particular lines or columns or even multidimensional columns, let's say. We had Fermi back in 2012 that was a 5D torus of topology. So each node was directly attached to 4 other in a 5-dimensional topology torus. Or there are more common topologies like the fat tree, where all the nodes are attacked to the first level switch and they see all their neighbors. Then those switches are attacked to a second level switch, and so we go until the master switch connects everything. This is more standard, and there are some variations like Dragonfly that is used now clusters today, where every node has not only one first level switch but has multiple of them, and there is a more detailed and sophisticated connection. I discussed the problem of memory access. This moves us immediately to the problem of I/O. And so also the file system is important. File system is how the input and output is organized, how our files are arranged inside the environment. So it is important to have a parallel file system that is capable of making all the tasks of the processors read and write at the same time. For example, I may want to write a file where every CPU is in charge of writing from line 1 to line I, let's say, and a parallel file system can handle this kind of task without much loss for the I/O performance. In our cluster, for example, there is a home file system that is not thought for this kind of stuff. It is more for compiling, for doing the basic stuff. And there are parallel file systems. And you can really see the difference if you try to ask for a really demanding computation in terms of I/O, and you write everything in your home and you write everything in our work area. The difference is no. So one of the most important parts of working with HPC, especially if your application is I/O dependent a lot, is to keep in mind that the file system is important. We put everything together. Imagine this like a compute node. Imagine that there is a bunch of memory, which is common. Imagine that all the processors which are made by core and now usually also vector unit for auto vectorization. There is a single core. The processor is a set of those cores. Usually there are 1 or 2 compute nodes, which are actually number of processors in a single unit, let's say. You can imagine a bunch of memory. You can also imagine accelerator. I didn't discuss it, but GPUs are also playing an important part in this scenario. You can imagine everything linked with a high performance network and a file system below it. This is more or less a scheme of how a standard supercomputer presents itself. And then the problem of software. You can't just run your standard PC application in a supercomputer. You have to think parallel. The most difficult part when working with parallel programming is to think parallel. Imagine that many CPUs are working, or even GPUs are working at the same time. And needs a change of mindset and also using the proper tools. So we need libraries, language extensions, we need everything that is suited for performing this kind of task. Behind all of that, the main programming languages are the plain old Fortran and C or C++. This is because they are procedural and they are low level, not exceedingly low level. It is not assembly, but at least they are not as high level as Python or other interpreters that are more abstract than this, because we want to deal with performance and stuff like knowing the memory address of the array that I am creating is important, because I want, for example, that the sequential items are analyzed one at a time. And so we have to manage cache. I have to deal with all those low-level aspects for which I need a low-level programming language. Upon this, many possible parallel programming paradigms are built. I will focus, you will see a lot of other, I don't know if maybe every one of these in a way or another during the rest of the school. As far as I'm concerned, I will deal with the first one here, which is MPI, which is probably here it is written the most difficult. I don't know about that, mainly because I don't know all of them. But surely it is requiring a lot of attention, because it is the one that gives you the most control over what you are doing in terms of communication. You are explicitly telling the system that you want that specific array going to that specific processor to that other specific processor with a certain amount of data changed and so on. So you have the sensation of control. And also it is distributed programming, while others like OpenMP are shared memory, and you will see that later with Moreno. This other example. So if you have decided your programming language and your programming paradigm, at that point you have to build an algorithm. And there are many examples. We can work with the master slave. You can say slave anymore, actually. I was told you have to say master worker now. The master is a task, a process that is dealing with handling the work to the other that are the workers. So worker A, take this data and perform some computation on it. Worker B, take this other data and give the results back to me. I will give you some other data, and so on. This is one example. There are other examples where the work is more shared. The domain decomposition is what I was saying about weather forecasting. Each task is a cell of the grid, and I want the neighbor grids to communicate, to share the situation in the border. Or I can work with meshes. It is a more engineering stuff. I'm not really, I don't really know much about it. I think that the idea is that I can concentrate my work in the part of my scheme that requires most computation. So I don't have standard shells or square-sided shells, but I have meshes that are focusing the computation in the part where it is required the most. And the most important slide of them all, we will also explain better in the next days. It is not guaranteed that when you have your parallel code, the faster, the more processor you put in it, the faster it goes. Because after a certain point, it becomes important the communication cost. How much time I am spending in making each process communicate instead of performing data work. If I use too much processor and my code is not that linear in scaling, it is possible that after a certain point I will reach a peak. And after that peak, my performance is going down. This is what we call scalability, the performance of my code depending on the number of processor I get. And this is another metric called the speed up that is more or less can be derived one another. The idea is parallel performance divided by serial performance, one core performance, more or less. And this also gives you an idea of how my performance is going. So an important thing if you are doing research and you have your parallel code, and you also are in a brand new cluster, because this graph will not always be the same from a cluster to another, because architecture also matters. In any case, the first thing to do is performing that, performing scalability tests. Check what is the combination of cores, of threads, of anything that gives you the best performance in your scenario. There are discussions about GPUs. I won't do that because I'm not really a GPU expert, and I think that there are many people that are more expert than me, even Chineka colleagues, but also other people. I suppose you will exit from this school with a vast knowledge of GPUs, so I'm skipping that one for the others. Now we discuss a little bit about HPC, but before that we discuss a bit about what is going on in the world. The most important unity of measurement when working with supercomputers is FLOP, floating point operation per second. How many operations with real numbers I can perform in a single second. This gives us the possibility to take all the supercomputers in the world, at least those who apply for that ranking, and created the top 500, which is the list of the 500 most powerful supercomputers in the world, of course. It is published 2 times a year, in June and in November. Here we highlight the June 2022 top 500 because it was very important worldwide. It was the very first time that a cluster reached the performance of exaflop. Exaflop meaning billion of billions of operations per second. This is the number that you need to check. It is expressed power in terms of teraflops. So 1 million, etc., means 1 exaflop. The second one was less than half of it, 400 petaflops. And the third one was European, and that is also important. Lumi in Finland, able to perform up to 150 petaflops, million of billions of operations per second. And then the others, Summit was number one for a while until those three came together in the same ranking and overpowered it. And there are others. So these are more or less some data about that supercomputer, Frontier, located in the University of Tennessee, if I recall correctly, 1.1 exaflop, 6.88 exaflop in mixed precision, because the impacts for AI work differently, because AI doesn't need long and double precision in their operations. 9,000 nodes and other information, 40 megawatts of power, and over to power. 21, it was probably the power expressed while performing this benchmark, I think. And also, it is not the maximum because Fugaku does more and performs less. The energy consumption is actually a great topic, and it is, I think, the most important topic today when working at performance computing, because we are reaching a point where many supercomputers that we have in mind can't be done simply because they are not sustainable. So this is a part of the statistics of the table that has to be always checked. There is also, I don't remember if there are slides in that, but there is also a sister ranking of the top 500 called the Green 500, where all those supercomputers are rearranged in terms of flop per watt. How much can I perform by consuming as less as possible? So this, I think and I hope that that ranking will become more important than the top 500 soon enough. Now let's talk a bit about Europe. At the beginning of this decade, at the beginning of the 20s, a joint undertaking from Europe called Euro HPC founded 3 supercomputer sites in Europe and tasked them with the goal of creating a supercomputer that was pre-exascale, meaning that it wasn't able to perform exaflop, being exascale, but it was able to get close enough to make us able to study technology that may one day give us exapop power also in Europe. Exapop is important because it is the power needed for a lot of particular research. For example, I don't remember how it's called at the moment. There are runs that you can perform when there is an emergency. Urgent computing, that's the name. You can perform when there are emergencies, like a tsunami affecting a population, some kind of thing. You can shut down the cluster for all the other people, immediately run, configure the full cluster to perform simulation of all the possible scenarios and locate what has the highest probability and intervene directly on the scenario that your supercomputing is telling you will be the likely outcome. That is able to prevent a lot of damage done by natural disasters. Or human brain. There is a project called Human Brain Project, and there is a theory that says that people are gathering information at the same speed, at the same process. Let's say we think at the same speed of the hexapop. This is the way I can say it. We can gather information at that particular performance. So people who are studying this kind of stuff are really interested in having hexapop in their mind, in their hands. So having that is important. It's important also for Europe that funded these free pre-exascale clusters. Finland, that was already in top 500 back in 2012, 22. Mare Nostrum in Spain, and finally the famous Leonardo from Italy that ranked first in November 2022, ranked for the first time in November 2022 and reached fourth place. Leonardo was the fourth most powerful supercomputer in the world. You see that Lumi, meanwhile, didn't stay in the hand doing nothing, but improved. But also Leonardo was there with 174 petaflop and was able to reach number 4. And the final ranking, published today, June 2024, makes us in 7th position. Lumi decreased a little, even if it improved. Leonardo also improved, 241. And there is Switzerland with their own supercomputer that appeared out of nowhere and took the 6th spot. Meanwhile, Frontier is still the only one exaflop declared supercomputer. And actually, no, it is the second because there is Aurora now. And also there was Eagle, which is 500 petaflop, all from the United. And then the Japanese, like before. Now, for Cineca, this is the roadmap. It was also the roadmap of my time in Cineca because I was hired more or less at the beginning of that line. We can see that in the last 12, 15 years, we moved in different systems. Fermi was the very first supercomputer back in 2012, able to reach the top 10 of the top 500, ranking number 7. It was 2 petaflop, which is not much if you think of it today, but it was relevant at the time. So it also shows how fast the supercomputing world is improving. Then we had Marconi. We currently have a little part of Marconi still installed. And Marconi 100, which was important because it was the first cluster where every node has 4 GPUs attached to it. It is now dismissed because it has to make room for a different cluster. This line is the moment where we moved from having all our machine room in Casalecchio di Reno in Bologna to having the Technopole. Technopole is a particular pole set also in Bologna, asked by the ECMWF, the principal European weather forecasting center. They wanted to deliver because they were all located in Great Britain and they can't do that anymore. So they deliver a lot of some of their data and of their machines in this Technopole, and Cineca also took advantage of the situation and installed there our current most important cluster, which is Leonardo, with the goal of reaching exaflop in the near future. So how is Leonardo made, composed of? What is Leonardo? What is Leonardo's architecture? There are two partitions, or we can say modules. The booster partition is the most important. We are almost 3,500 nodes with 4 GPUs, 800 each, which are top of the game. At least they were at the moment of the installation, but they're still very perform. 512 gigabyte RAM per node, and this is the part that gives us the most peak performance, and is also highly required, for example, by AI engineers. Yep. It is mostly the first. When you say when I say that in top 500, I get one performance, and then the next time I get another performance. It usually is because the first ranking is more or less incomplete in the sense that some places are still, some pieces are still missing, but we want to go to the top 500 anyway because we need to hurry. So clusters, let's say that before it wasn't like this. The first ranking was the best ranking because you couldn't move over than there, and the architecture is there. How to use it efficiently is already known when you build it because builders tell you or give you hints about how to use it. So the software level, let's say that is not that relevant in terms of finding the peak performance. What matters a lot now is finding a way to add more. So for example, when we performed the first ranking of Leonardo, we didn't have the full booster partition. We still had like 75% of it. Then we added the rest. Then we added the data-centric partition, which is the other partition. Actually, it didn't that much because it was only CPUs, but it added that little that was helping. And we are working to get a third addition that we are still not really. We still don't know much about how it will be. I think it will help AI people that are high requesters of our cluster, and that also will be added to the count. At least this is how Cineca performs it, but I think that for the other centers it's more or less. Yeah, there is the most common benchmark, which is the high performance LIMPAC, which is basically a system of differential equation that has been used as a standard since the birth of top 500, at least I think 80s, 90s, more or less. And the point is not the solution because it is known. The point is how do you perform when you gather a solution. The full cluster is dedicated to perform the LIMPAC. There are engineers working on tweaking and tuning the single GPU and the single node and the single cable in order to get the best performance possible. And when you have the number, you submit it to the top level. Well, we have different partitions and they can't communicate with each other. At least it is not easy. With Marconi, we tried. We had different partitions and we made them communicate between each other, and the result was a hell for everybody involved. Now, what we do is separate the partition. Actually, now that I think about it, it is possible that that number in the top 500 is GPU only, because I think that Leonardo CPU was submitted as a cluster on its own, like così ranked the 100 and so something like that, because it changes CPUs. So no, mixing the architecture is not a good idea because you don't know where you are going, and your improvement is not necessarily a lot. Yeah. Apart from that, Dragonfly, which is a variation of patch-tree topology, infinite network of up to 200 gigabit per second, and over 200 petabyte of storage. There is a fast tier where the file system is very fast, but there is a small capacity, and a more general purpose tier that can give you the space for a lot of data. There are now AI applications that are asking for petabyte of data. We can't always grant it, but the request is high. I think I have the last slide, which is another comment of the thing that I was saying in answering some of you. The importance of energy consumption, which is becoming important because, for example, we thought we as the world reached the petaflop in 2008. We thought that the 10 years after, in 2018, we were able to reach to exaflop. It took longer than expected, and the Frontier was able to do it in 2022. This is because we can't think anymore, I just add new hardware and exaflop is done. Because even if that were true, it is not sustainable anymore. It costs too much energy, and it is a problem also for the environment, because the more powerful my supercomputer is, let's say that is a larger version of the transistor problem I was saying at the beginning. The more I perform, the more it is likely to get damaged, overheat, the more the cooling system has to work continuously, and it costs me too much, and it is affecting the environment too much. And that's not sustainable anymore. So there are studies now. Most of the high performance computing future technology is working. The most common problem is dealing with this kind of aspect, and so there are energy efficient cores. GPUs are great also because they perform a lot, and they're not that heavy with environment, with energy consumption. Novel cooling system. Leonardo, for example, is not air heated, but it is water heated, water cooled. Sorry, the opposite. Water is passing through inside the compute nodes and through the processor to cool it instead of air, so we can recycle the water, and this is a lot is efficient and also less costly. Job monitoring and scheduling at the software level. There are a lot of users that are trying to understand not only how many compute hours I am spending with that particular job, but also how many kilowatt am I consuming, how many watts I am consuming. It is becoming important, and also provide scheduling, for example, trying to get the nodes that are close to each other so they spend less time in communication. This kind of stuff can help also in terms of energy consumption. Machine learning doesn't need high level precision, so there are architectures that are now built with low level precision in mind, and that is also helping, and all this kind of stuff. So yeah, the main goal now of high performance computing is to finally be able to work towards the success of creating the most powerful computers possible without being too impactful on the environment. And that is all, more or less.